confidence intervals for population means. Our objective, we're going to construct using StatCrunch and interpret a confidence interval for a population mean. All right, let's talk about those things we know that are going to come into play here. We know what a point estimate is, the value of a statistic that estimates the value of a parameter. We know what a confidence interval is, a range of values in which we are fairly sure our true value lies. Confidence intervals are of the form point estimate plus or minus the margin of error. We know what level of confidence means, a percent that represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. Common levels of confidence include being 90% confident, 95% confident, and 99% confident. We know what margin of error is, the difference of the upper bound of the confidence interval and the lower bound of the confidence interval divided by 2. Okay, it's the distance between the point estimate and either the upper bound of the confidence interval or either the lower bound of the confidence interval or the upper bound of the confidence interval. It is also a measure of how accurate the point estimate is. And finally, if we are not told the data set is normal, we use either the central limit theorem, more than 30, sample size greater than 30, or we use the normal probability plot combined with the box plot to assess normality to see if we can move forward. Okay, the mean is not a proportion. Okay, go figure, right? So we're going to be using a different, if we were using tables, we'd be using a different table. The T-chart, I believe we'd be using, as opposed to the Z-table, or the T-table as opposed to the Z-table. In StatCrunch, we were using proportion stats with proportions. We're going to use T-stats, T-stats, one sample. Again, T-table is where this all comes from. So we're going to use StatCrunch's T-stats to construct the confidence interval for the proportion mean. Okay, we're now on the mean. As a reminder, and we've spoken to this previously, a 95% confidence interval indicates 95% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the true value of the parameter. What it does not mean is that there is a 95% probability that the interval contains the true value of the parameter. You have one interval. It does not mean there's a 95% probability that that interval contains the true parameter. Okay? So, as usual, I think some examples will help, and I believe I've got 3 lined up. Maybe I've got 4. No, I've got them misnumbered, that's why. So let's put a 2 here, and let's get ourselves going. I forgot to number these correctly as I was making the draft. My apologies, we'll be fine. Okay, get my notes together and get my StatCrunch ready. I hope we're going to be using their T-stats, calculator. A simple random sample of size n is drawn from a population that is normally distributed. That's important to know. This population is normally distributed, so we don't have to worry about the central limit theorem. We don't need to worry about the box plot and outliers. We don't need to worry about the normal probability plot because it tells us the population is normally distributed. The sample mean x bar is found to be 50. The sample deviation S is found to be 8. Okay, use StatCrunch to construct a 95% confidence interval for the population mean, mu, if the sample size is 20. Okay, letter A. So let's put A down here. We know that X bar is equal to 50. We know that the sample standard deviation S, and I usually use a lowercase cursive s because my s's look like 5s, is equal to 8. We know that our sample size is 20, and we know that 98% is the same thing as 0.98. Okay, so let's go into StatCrunch, and we'll use this right here and put that data in to come up with a 98% confidence interval. All right, StatCrunch. And still need to, I hope it's focusing. I believe it's focusing. Okay, we go back, we're gonna go into stat. And this time we're choosing t-stats because it's based upon what's called the t-table. And we're still doing one sample. And in this case, the data is already summarized. It's not a bunch of raw data points. So we're gonna, with summary. Okay, what does our sample mean? Our sample mean we said was 50. What is our sample standard deviation? 8. And our sample size is 20. Scroll down. We want to perform a confidence interval for the population mean. So select that option. And we want to be 98% confident. So we're going to choose we're going to change the default 95 to 98. And we're now going to compute. And here you have it. Okay, there's our sample mean. We already knew that. Our lower limit is 45.457 and our upper limit is 54.543. Excuse me if I round that. Let's go back to here. Okay, and we say that our confidence interval, and I'm just going to write it as an interval, is a low of 45.457 and a high of 54.543. So what does that mean? We are 98% confident, right? That the population mean, I'll abbreviate population POP, the population mean, which we know is mu, is between 45.457 and 54.543. Okay, letter B. Use StatCrunch. Construct a 98% confidence interval. The sample size is smaller at 15. How does decreasing the sample size affect the margin of error? Let's see. So back into StatCrunch. I've already got it open. I need to edit it though, so I'm going to go into Options, Edit, and the sample size has gone from 20 down to 15. And everything else remains the same. We'll compute. And the confidence interval's lower limit is 44.579, and its upper limit is 55.421. Let's write that down. Okay, so our new interval. So when n is equal to 15, that gave us a new interval of 44.579, a new low limit for our confidence interval, and a new upper limit of 55.421. 55.421. So we notice when we had a larger sample, our confidence interval went from 45.5 to 54.5. With a smaller sample, our confidence interval widened to 44.5 to 55.4. So, how does, you can't see that if I don't show it to you, letter B. How does increasing the sample size affect the margin of error? Well, it increased the margin of error. So a decrease in sample size increases the margin of error. And that makes sense. Your error is going to go up with a smaller sample. Letter C. Use StatCrunch to construct a 95% confidence interval. So we were doing 98, now we're doing 95 for the population mean if the sample size is 20. Compare these to part A. All right, letter C. We want to go with from 98 to 95. So we want to go with 95%. Okay, and let's see what happens. So we'll go back to StatCrunch. And I'm going to go to my options, edit, and let's see, we're still doing 50, but we're going back to the sample size of 20. We want to hold that constant, yet we want to change our confidence interval to 95%. Okay, so I'm going to change that to 0.95 and press compute. And my lower limit goes from 46.226, and my upper limit of the confidence interval is 53.744. Okay, so I'll make sure you can see the C part up there while I write. When I do 95% with, and let's note that we're back up to a sample size of 20, and it's 20, so we can compare it to this one. So we kept this the same, but we changed this time in letter C. Our confidence interval changed to 46.256 as a lower limit and 53.744 as an upper limit. So we decreased our confidence, okay? We decreased our confidence, which means we're going to decrease our margin of error. We're going to decrease the size of the interval, which makes sense. I'm less confident, but I have I'm less confident because I'm pretty tight in there. Okay, so a decrease confidence interval, I'll abbreviate that CI. You are decreases the margin of error. Okay, letter D. Could we have computed the confidence intervals in parts A through C if the population had not been normally distributed? Okay, well, the answer is no. Okay, first off, our sample size is too small, and we're unable to calculate the QQ plot or the box plot to check. Okay, so the answer here is no. Okay, sample size of 15 or 20 is definitely less than or equal to 30, and can't calculate, I think because our data is all summarized, we can't calculate it. Can't calculate the QQ plot, the normal plot, or the box plot. Okay, well, I think box plot, I think they use 2 words for box plot. So there you have it. Okay, let's continue. More examples will always help us. I got 2, wait, I go to the back of that page. Sorry about that. Number 2. And I goofed on my paper. Hopefully your paper's right, but I put a 3 there. Okay, I'm gonna get my StatCrunch ready and turn my other paper over. Okay, think I'm ready. A random sample of 51 fatal crashes in 2017 in which the driver had a positive blood alcohol concentration called BAC from the National Highway Traffic Safety Administration results in a mean BAC from the sample of 0.167 grams per deciliter and a standard deviation of 0.01 grams per deciliter. Okay, a histogram of blood alcohol concentration in fatal accidents shows the BACs are highly skewed right. Explain why a large sample size is needed to construct a confidence interval for the mean BAC of fatal crashes with a positive BAC. Okay, why? Okay, it must be large. I'll explain why a large samples. Okay, it must be large. Explain why it must be large. Well, it must be large, which we mean greater than or equal to 30, so that, as we've learned, so that the distribution of the sample mean will be approximately normal. Okay, so we weren't told it's skewed right, but a large sample is needed because that means the distribution of the sample mean will be approximately normal. Even though the distribution is skewed, if we get above 30, the sample mean will become normal. Okay, letter B. Let's see here. In 2017, there were approximately 25,000 fatal crashes in which the driver had a positive blood alcohol concentration. Explain why this, along with the fact that the data were obtained using a simple random sample, satisfies the requirements for constructing a confidence interval. Well, one of the requirements is that the sample size must be less than 5% of the population. Well, 25,000 is way less than 0.05. Our population, even population of drivers, is probably 250 million, and that's just an estimate. So we're good. Okay, we're good with that one. Letter C, use StatCrunch to determine a 90% confidence interval for the mean BAC in fatal crashes in which the driver had a positive blood alcohol concentration. Okay, well, we know that our sample size is 51. We know that we came up and our sample mean, X bar, is 0.167. We know that our sample standard deviation, S, it tells us up there, is 0.010. And we want a 90% confidence interval, and 90%, of course, is equal to 0.9. Let's go to StatCrunch with this information and let it do the math for us. Okay, back to StatCrunch. Remember, we're doing the population mean. So we're talking about we're talking about using the T-stat. T-stats, I'm going to repress it. With this, our data is summarized. So with summary, it's one sample with summary. Okay, the sample mean, 0.167. Hope I get that right. The sample standard deviation is 0.010. And our sample size was 51 crashes. We'll scroll down. We want to perform a confidence interval. We're not performing hypothesis tests yet. We want a 90%, so we'll change the default 95 to 90, and we'll go up here and we'll say compute it. And there we go. Our lower limit is 0.165, our upper limit 0.169. Okay. Go back to letter C here and make sure you can see letter C up the top as well. Okay, so our confidence interval, the lower limit is 0.165, the upper limit is 0.169. What does this tell us? We are 90% confident that the mean, the population mean, right? Let's say the population mean BAC, blood alcohol concentration, in fatal crashes in which the driver had a positive blood alcohol content. So the mean BAC in fatal crashes is between 0.165 and 0.169. We're 90% confident that's the case. Okay, so we're 90% confidence between these two. Let's look at letter D. If we use a blood alcohol concentration of 0.08 as legal intoxication, is it possible that the mean of all drivers who are found is less than this legal limit? Well, we just did this, and we're 90% confident this is between these two. Okay, so it's always possible. 0.08 is way down here. Okay, so it's always possible. Of course, it's always possible. Again, statistics is not about certainty, so it's always possible, but in this case, it's not likely. We're 90% confident that the average for the population is between these two numbers. To go all the way down to 0.08, which is significantly, it's half of this, is significantly lower, it is possible, but it's not very likely. All right, one more example for us. And we'll make use of StatCrunch again, if I'm not mistaken. I think I got to put the data in this time. Okay. I think we'll do that. Yep. All right, let's see here. Travelers pay, example 3. I still got a 4 up there for you. Travelers pay taxes for flying, car rentals, and hotels. The following data represent the total travel tax for a 3-day business trip in 8 randomly selected cities. Okay, well, 8 is certainly fewer than 30, and we're not being told in that first couple sentences that the population is normally distributed, but we are told in the note, a normal probability plot suggests that the data could come from a population that is normally distributed. In addition, a box plot indicates there are no outliers. We can move forward and construct a confidence interval. Okay. Enter the data into StatCrunch and use StatCrunch to determine the sample mean travel tax, and we should only have 1x on travel tax, and the sample standard deviation. Okay, let's do that. These are our 8 numbers. Let's put that into StatCrunch. We'll have it do the math for us. And I'm going to delete this one here. And I'm going to put the data in column, I want to put it in column var1. And give me a moment, let's do that here. So $67.81, 6781, go to the next one. 7869, $78.69. The next one, $68.99. Whoops, that should be a period, not a comma. Number 4, $84.36. Hoping I'm not making any mistakes. The fifth, $80.24. The sixth, $86.14. The seventh, $101. That's kind of high. And 27 cents. Wonder what city that came from. And the last one is also fairly high at $99.29. So there we have it. Okay, got to get up. I got to find a way to get up here. Oh, there we go. This way. Okay, let's do a quick refresh because mine's not getting it. Oh, I just lost it. Okay, let's try again. Sorry about that. Okay, 67.81. Again, good thing there are only 8 of them. 78.69. 68.99, 84.36, and then 80.24, 86.14, 101.20. Oops, press the Q. 101.27, and last but not least, 99. I hope I get it this time. 99.29. All right. Okay, we'll do that. Now let's go to our stat summary stats. Oh, now it's not getting it. I got to get back to it. Okay, let's go to stat summary stats. We're doing the column. Want to select column 1. Okay, it's already defaulting to all the statistics. Let's just compute them. I need the mean and the standard deviation. The mean, 83.349, and the standard deviation is 12.324. So let's note that, because we need the mean and the standard deviation for the sample in order to put it into the t-stat, into the t-calculator. So we entered the data, and we came up with X bar, our mean of $83, and I went out to 3 decimal places, 349, and we came up with our sample standard deviation of 12 point, and let me check it again to make sure I have it correct, 324. Okay, use StatCrunch to construct a 95% confidence interval. Okay, so let's see here. We have a sample size of 8. We know the sample mean is 83.349 to 3 decimal places. We know the sample standard deviation is 12.324, and we want to have a 95% confidence interval, and we know that 95% is 0.95. Let's go to the calculator. So go back to here, and I can delete this one, so options delete, and I can go to the calculator, which is t-stats. Again, we're doing population means. We're using the t-table behind the scenes. One sample with the data is summarized. We already have the mean and the sample standard deviation. The mean, 83.349, 83.349. The standard deviation, 12.324. And the sample size was only 8. We're okay. We tested it for normality and we were good. We want our confidence interval to be 95%. Well, that's the default. That worked. Let's compute it. Okay, the lower limit, 73.046. The upper limit, 93.652. Okay, back to here. And we can answer question B. Okay, construct a 95% confidence interval. Our 95% confidence interval is 7.3, goes from a low of $73.046 to a high of $93.652. And so what are we saying? What does this mean? Okay, we are 95% confident, right, that the population mean, okay, the mean paid for a 3-day business trip to any cities is between, and I'll round this to money, $73.05 and $93.65. That's what it means. Okay, last piece, so we're all done. Letter C. What would you recommend to a researcher who wants to increase the precision of the interval but who does not have access to additional data. Well, increase the precision means decrease the width. That's what it means. You want to be more precise. You want to have a smaller width, okay? Well, if we want to do that, if we want to decrease the width of the interval, we need to decrease the level of confidence. Okay, so I would decrease the level of confidence because that will increase the precision. It will, and the same, it will decrease the width. So decrease the level of confidence to say 90%. If you go to decrease the confidence level, I'm not so confident, you'll have a more precise, closer in interval. You have decreased the width. A lot there, but a lot of examples for you, all about confidence intervals and using the t-stats functionality in StatCrunch to come up with them.